Hello everyone and welcome to another math tutorial. This video will continue our discussion on circles, and specifically we're going to go over three theorems in this video that utilize chords to find lengths and arc measures. Let's take a look at our first theorem. Alright, our first theorem is called congruent corresponding, Alright, we're going to redo this one. Okay, the first theorem is called congruent corresponding arcs theorem. And it states this, that in the same circle or congruent circles, two minor arcs are going to be congruent if and only if their corresponding chords are congruent. So utilizing the picture, this theorem says essentially that if AB is congruent to CD, then arc AB is congruent to arc CD. Okay, let's look at a couple example problems to help illustrate this theorem. The example slide for congruent corresponding arcs theorem has got a couple of example problems on it. First problem says that if the measure of arc AB is 110 degrees, find the measure of arc BC. So we know the value of the arc from A to B, 110. We're looking for the value from B to C. What we need to be able to recognize here is that we've got two chords that are congruent. They're both measure 9. And because those two chords are congruent, that means that the two arcs that they intercept are also congruent. So if arc AB is 110 degrees, that means the measure of arc BC is also 110 degrees. The second example problem, and keep in mind this is a completely different problem. So when this says find the measure of arc AB, it's not 110 degrees like it was up here. So just ignore this problem up here. We're now doing this problem, but we're going to use the same picture. This problem says that the measure of arc AC is 150 degrees. So from A to C, right there, that's 150 degrees. I want to find the measure of arc AB. Now what we have to know, just like in the last problem, that these two minor arcs were congruent, same information. We have to know that AB and BC are congruent. But we don't know what they are, that's okay. But as long as we know they're the same, we can identify AB as x degrees and BC as x degrees. Well, now with those two arcs and arc AC, this 150 degree arc, we have the entire circle all the way around. And we all know how many degrees make up the entire circle. So we're going to write an equation relating these arcs and the entire circle. It'll be x plus 150 equals 360. And take my 150 and subtract it from both sides. So we've got 2x equals 210, and divide both sides by 2, x equals 105. Our next theorem is called perpendicular chord bisector theorem. And it states that in a circle, if a diameter of a circle is perpendicular to a chord, so let's highlight that right here. We've got the diameter that's perpendicular to the chord. Then that diameter is going to bisect the chord and its arc. So because that diameter is perpendicular to the chord, that means that the chord is bisected and this arc is also bisected. All right, let's look at a couple of example problems to illustrate this particular theorem. All right, on this example slide, we've got a couple of problems, a couple different measurements we're asked to find. The first one is to find CE. So CE is the chord from C to point E. What I noticed by looking at this is that BD is a diameter, and also this is the important part, that it is perpendicular to the chord. And because it's perpendicular, that means that this side of the chord is congruent to this side. So if it's 5 here, it's also 5 there. That's going to make CE 5 plus 5, and CE is going to be 10. Now also, because that diameter is is perpendicular to the chord, that means that these two arcs, or this single arc has been bisected, or that these two arcs are congruent. So when we're trying to find the measure of arc CE, we are going to be able to set these two arcs equal to each other because they're congruent. So if I do 9x equals 80 minus x, I'm going to take that minus x and I'm going to add it over to the left-hand side. So I've got now 10x equals 80, so x equals 8. Now, x equals 8 does not solve the problem, but it does allow me to finish the problem. I can put that value of 8 right here, so that 9 times 8 makes this arc 72 degrees. A good check would be to plug it into the other arc because they should both be 72 degrees. So if I put 8 in for this x, 80 minus 8 is also 72 degrees. And so the measure of arc CE is going to be 72 plus 72. It's going to be 144 degrees. The final theorem in this video is called the equidistant chords theorem. And this says that in the same circle or congruent circles, two chords are going to be congruent if and only if they are equidistant from the center. These two chords, CD and AB in this picture, are congruent chords if the chords are the same distance from the center. So if this distance right here is the same as that distance, then according to this theorem, these chords are congruent. So we're going to do a couple of example problems with this particular theorem. They're a little bit different examples, so I want to take a look at two of them. Okay, our first example problem of this equidistant chords theorem asks us to find the radius of the circle here. First off, there is no radius drawn anywhere. Like, the radius is going to be a segment from the center to a point on the circle, and nowhere is that drawn anywhere on the circle. So we'll come to that in just a little bit, but let's take a look at what we have and see if there's some math that we can do based off what we have, and maybe that'll lead us to finding the radius. Now, when I look at this and I'm thinking of the theorem that we just presented, I see this, the first thing I notice is that these two lengths right here are congruent. They're both 3 units, okay? Well, that's the length from the center to each of the two chords. Because those lengths are the same, that means that the two chords, DF and AC, are themselves congruent. And so if these two chords are congruent, that means I can take these two expressions and I can set them equal to each other. So that's a thing that we can do. Let's go ahead and do that. If I equal 5x minus 2 to 3x plus 2, and I solve this equation for x, I'm going to take this 3x over to this side. I'm going to take this minus 2 over to that side. And the result then is 2x equals 4, so x equals 2. All right, so x equals 2, that's something, it actually is helpful. It's not the radius, it doesn't solve the problem, but it's going to unlock some means to solve the problem. If I take that value of 2, and let's just say that I substitute it in right here, that's going to give me 6 plus 2, or 8. And if you want to check, you can put 2 on this side as well. That's going to give me 10 minus 2, which is also 8. So the fact that x equals 2 does check out. I am getting the same length on both of these two chords, like we should. Now let's worry about finding the radius. Okay, now the radius is a line segment from the center to the circle anywhere. If I conveniently draw my radius to go from center to one of these chord endpoints, like so, what I've now created is a right triangle. And we could use Pythagorean's theorem to find the length of the radius. So what do we have? We have one length of 3. Since this entire chord was found to be 8, that means the other leg is 4. So now we're needing to find the radius there. And if you remember that 3, 4, 5 is a Pythagorean triple, well, that then identifies the radius for you. If you don't remember that 3, 4, 5 is a Pythagorean triple, then you can certainly work out Pythagorean's theorem. 3 squared plus 4 squared equals r squared. And you can do the math to show that r equals 5. And that completes the problem. Okay, this final example is presented just a little bit different as far as what's given. So I want to include this example. When I look at this circle, first thing that kind of stands out to me that's different than the last one is the last one gave me the distance from the center to each of the chords. And it gave me that those lengths were the same. And this one doesn't. This gives me algebraic expressions for each of those distances. So I don't know that these distances are the same right out the gate if I'm only looking at the picture. But I do have some extra information that's up here, and this information is going to be pivotal to solving this problem. Mainly this part right here. This is what's needed. Hold that JK, this length here, is equal to LM, and that they're both equal to 24. So I know that these two chords are congruent. So that equidistant chords theorem kind of in converse form is at play here. What I can do is kind of reverse the logic in that if these chords are congruent, then that means the distance that they are from the center is also congruent. So I do know now that because of this, I do know that this length 3x is the same as this length 7x minus 12. So we can equal those to each other. 7x minus 12 equals 3x. If you like, we can move the 3x over to this side. I'll move this minus 12 over to that side. The result of that is going to give me 4x equals positive 12. So x equals 3. Now, we need to find the radius. So let's see where we can go with this. The radius, again, like the last problem, it's not drawn in, so we need to go ahead and do that. We could maybe draw it in right here from n to k if we want. So there's our radius. We need this side of the triangle and this side. First off, the 24 can be used right now. If we divide 24 by 2, gives us from p to k is 12. If we take the 3 and plug it in for the x, 3 times 3 makes this length 9. And we've got a right triangle now with legs 9 and 12, and we can find the radius. So when I look at this, if you notice that this is just a 3, 4, 5 right triangle like the last one, where the measurements are being scaled by 3, then you can certainly use that. 3 times 3 makes 9, 3 times 4 makes 12, 3 times 5 makes 15. That's our radius. If you don't see that 3, 4, 5 triangle there that you can scale up, then by all means just do 9 squared plus 12 squared equals r squared and solve that for r to be r equals 15. I'll leave you to do that math if you need to do it or if you'd like to do it to confirm. Okay, that completes this video on using chords of circles to find lengths and arc measures. If you have any questions, please leave a comment down below. If you found this video helpful, please give it a thumbs up to help support the channel, and I'll see you in the next one.